I don't work in computer science. On the other hand, I use a lot of linear algebra. And so some years ago, when I found out that the Google algorithm uses very nice bit of linear algebra, I decided that I could use this to proselytize, make propaganda for linear algebra, because whatever you do with mathematics, you're going to need linear algebra. And also linear algebra, if you think about it a little abstractly, is a way of getting used to thinking about mathematics, not in terms of manipulating symbols and equations, but in terms of spaces and maps between them. So actually this is really the barrier that separates people who get mathematics and people who don't. That is, especially if you want to understand modern mathematics, you have to really think in terms of sets and maps. A function is a map from one set to another. You have two sets, and a function is a map that assigns to every element of the first set an element of the second set. And then these sets can have structures. For example, if each set is a vector space, then you could look at maps that are compatible with the vector space structure, and these are called linear maps. The study of linear vector spaces and linear maps is linear algebra, which you know from school days as the study of systems of linear equations. And a little later you think of them as matrices and vectors, and matrix multiplication and multiplying vectors by matrices. And a little more sophisticated way of thinking about them, about these things, is to think in terms of vector spaces and maps between them. So the whole thing, I got you here under false pretenses. Basically, I want to sell you on linear algebra, but I thought if I tell you, if the title was linear algebra, nobody would turn up. Whereas Google, everybody uses. So, and it's a pretty neat bit of linear algebra. I hope to convince you of that. Okay. Yeah. So the crucial thing that you must note there is the term page rank. So I hope to explain to you what the page rank is, and then I hope to explain to you how Google determines the page rank and the linear algebra that lies behind it. Okay, so we are from the old days desperately seeking information. So in olden times, if you wanted some information, you would go to the library and hope that you would find a relevant book, and then you would look at it, and well, if you're lucky, the book would have an index, and you would look at the index. And so to prepare this talk, I went into the library here. The CMI has a very good library. It has not just mathematics books, and I found this book edited by Ramchandra Guha. It's called Makers of Modern India, and I looked in the index for Jawaharlal Nehru, and I found a list of pages, which you see it begins from the smallest page and goes to the biggest page. It begins with 1, 4, the pages 8 to 10, 13, 187, and up to 523. So the index displays the pages in increasing order, and if you look at the page 1, you find it's in the preface. Page 4 is also the preface. Nehru's excuse me. Hello? Yeah. Nehru's name does appear in those pages, but there is not too much useful information. It would be much better if the first entry in the index was the most useful one. It had a lot of information about Nehru. Now, what the Google PageRank does is, it does this for pages on the web. So, you've all used the World Wide Web. The World Wide Web consists of sites, and each site has several documents called pages. And the pages, what's crucial about the web is that the pages have links from one page to another. Okay, these links need not be, it can be from one page to the same page, it can be one page to another page within the same site, or it could be from one page to another page on another site at the other end of the world. So these are called hyperlinks, and this is what makes the web so powerful. The web, as far as Google is concerned, is a collection of texts, pages, with hyperlinks between them. Okay? So Google exploits this structure of the web to determine its page rank. I still haven't explained to you what page rank is. We'll get there. So, but just to give you some idea of the task that Google accomplishes, here is the number of pages that Google indexes. These days it's 60 trillion, and unfortunately there are two meanings of the word trillion, but I think I've chosen the correct one. That translates into 6 into 10 raised to 13 web pages. So that means 13 different documents, not an actual page, but each page is a document. And every day there are 3.5 billion searches by web users. That translates into 3.5 into 10 raised to 9 searches. And what Google tells you that 84% of searchers do not go beyond the first 3 results in a search. So if you search for anything Ramanujan, you typically find what you need in the first 3 results that Google gives you, and if you don't, you give up. And most of the clicks that the web users do is for the top 3 search results. This is why there is such competition among advertisers to be among the top results. Okay? So there's a whole industry called search engine optimization that does that for you. So when you launch a search on Google, typing the word Ramanujan, for example, you get a list of web pages, and Google will tell you how fast it did the job. In fact, it posts, it's pretty impressive. I understand why they feel like boasting. You see, it's pretty fast. So here is the result of a search for Ramanujan on Google, and this was done a few months ago. I took a screenshot, and this is, you're all familiar with these pages. So the Google has 2 components. The first is something that's relatively pedestrian. We are familiar with it from books, and computer science has very efficient ways of handling these things. That's just an index. So first of all, okay, as I said, the structure of the web is that there are these pages which are distributed. They reside on servers distributed around the world, and Google has programs that crawl the web. They're called spiders or Google bots. I mean, in the old days, and now maybe the terms have evolved. Automatically, they go out, systematically they go to web pages and retrieve the contents, download the contents into huge, gigantic facilities, storage facilities that Google has. So these are the cached pages that you often read about. Google typically downloads whenever it can the contents and onto its own servers, and then it lets loose the programs which will go through the contents of the pages and form an index. So an index is just like a book. For every term, it's just a list of all the pages where that term occurs. So there's nothing very exotic about an index, except that the size of the index of Google is enormous. I mean, the number of, you're indexing a gigantic book consisting of trillions of pages. So every term will have a really long list of pages in the entry in the index. Okay, but and this is already pretty impressive. But computer science, there are very efficient ways of handling indices, handling indexes. But what's really crucial about Google is that every page has a rank, a weight, or if you want to think of it, marks in an examination. Except marks in an exam are given out of 100. A weight is a number between 0 and 1. And when you make a search request, what Google does is it first calls up from the index all the list of all the pages that contain that term or a combination of terms, and then it presents the results to you in decreasing order of this weight or exam mark or importance. So think of this weight as a measure of the importance of that web page, its significance, how likely it is to be useful to you. So typically there are, say, 1 million pages which contain the combination of terms you search for, and it gathers that list of 1 million entries, but it orders them in the decreasing order of the weight, and then it presents the results in decreasing order of weight. So how useful Google is determined by how good it is at assigning these weights. Okay? I haven't yet told you how these weights are assigned. That is the secret of Google. That is the secret of PageRank. That is where the linear algebra enters. Okay. So let me repeat. At the heart of Google is a gigantic index and a global ranking of all trillions of web pages. Okay. By associating to each page a weight. Okay. Now, so that's a bit hard to take in, but it's simple enough. Yeah. An index, and every page has a measure of its importance called its weight. Okay, and I have to tell you how this weight is assigned. Okay, any questions? Because now we're going to plunge into the page rank algorithm. Yeah. Okay, so to understand this, one considers a toy model of the web. So, toy models are used by mathematicians and physicists to understand very complicated phenomena by extracting the essential features of the phenomenon and making a model of that. Their toy models, in spite of the term, are very, very useful. And one should really take them very seriously, because if you understand them, this leads to really profound understanding. So one needs a toy model of the web, so which means a small scale version of it that we can sort of look at from all points of view and play with. So I'm going to present to you a toy model of the web where there are only 9 sites, and each site has only 1 page. So I repeat, there's a distinction between a site and a page, because, for example, the Chennai Mathematical Institute has a site where you will find many pages. There's a page that lists the faculty, each person on the faculty has his or her own page, and so on. So, but we are going to suppose, for simplicity, there are only 9 sites in the world, and each site has only 1 page. And then, of course, these pages have links between them, hyperlinks. So here is our mini web. So these are, so I should tell you that I gave this lecture some years ago in Rabat, in Morocco, and so I took a list of institutes in Rabat, and I made this mini web from those institutes. And I forgot how I made this graphic. So I wanted to replace the acronyms by acronyms of, say, CMI, IMSC, IIT in Chennai, but I forgot how I generated this graphic, and I could not do it at short notice. So I've just retained that. That is why you'll find somewhat strange, actually they look like French acronyms. They are indeed French acronyms. So here is a mini web. There are only 9 sites, 9 institutes. Each institute has its web page, and the web pages have links between them. So, this representation is what's called an oriented graph. A graph is basically a one-dimensional object consisting of points which are called vertices, which correspond to the sites and pages, and it's a directed graph. That means some of the sites, the vertices are connected to others by arrows. And an arrow represents a link from one page to the other. For example, if I look at this page, it has one link. This page refers to it. There is a link from here, this page to this page, and this page has 2 links going out to those 2 other pages. So I've just represented this mini web by an oriented graph. It's just a way of picturizing the situation. There's nothing fancy has been done here. Okay. So this is an oriented graph, as I told you. That means I've just told you everything that I've written in the first bullet point. The vertices stand for web pages or sites, because as I've said several times, I'm assuming that the sites are so simple that each site has only one page. And the arrows represent links between them. So in the terminology of graphs, one of these points is called a vertex, and one of these one of the arrows is an arrow. Yeah. Okay, now the aim of the PageRank algorithm is to list the pages in a way that the order reflects their importance in the World Wide Web. And it is up to us, or it was up to Brin and Page, the people who founded Google, to devise a method to do this. And the only criterion is that people who surf the web should find it useful. This is not a God-given rule. I mean, this is real. It's engineering. It's not science. Engineering means you come up with ways to solve practical problems by practical means. So, as I said, you have to devise a way of ranking web pages in a way that surfers find it useful. Okay, and this, as I explained before, we plan to do by attaching a weight to every site. And the weight should be a real number between 0 and 1. And the sum of all weights should be equal to 1. Okay. This is not, strictly speaking, it's not necessary, but for other ways of thinking about this, which I will come to in a minute, it's useful to assume that the total weights, the sum of all weights is equal to 1. It's as if you are marking people, the exam sheets of people in a class, and you decide that there are only 100 marks to be divided between all the people in the class, and you will divide them proportionally to how well each person performs. So rather than marking each person out of 100, you decide there are only 100 marks to be distributed between the class, and you give each person marks corresponding to how well that person does. So since there are 9 sites, so we are going to have a little bit of mathematical notation, and for mathematical notation, we work with numbers rather than names. So earlier I had all these acronyms, E and F and so on. I replaced the acronyms just by numbering the 9 sites in an arbitrary fashion, 1 to 9. And then, so the weights of the ith site I'm calling, the weight of the ith site I'm calling xi, and the condition that xi, each number be a real number between 0 and 1 is the first equation, and the sum is equal to 1, that's the second equation. Okay, so we want a method of associating this weight to each site, and the only thing we have that we can use which does not use the internal structure of each page. Okay? So this is the important thing. The Google algorithm does not use artificial intelligence. I mean, it's not that there are computers that read the content of a page and decide, this looks interesting and useful, so this should rank high. No. The only information that the Google algorithm uses is what the rest of the web thinks about each page. You understand? So that is all. So as far as the Google algorithm is concerned, once you represent the web by the directed graph, you can forget about what is the content of each page. Because, as I said, you don't have machines smart enough to make judgments on our behalf. The only thing the machine can do is to work with the data it has, which is the links between pages. Okay? So now let's think about this for a second. How can we exploit the links between pages to give each page a measure of its importance? Well, clearly, the more pages link to a page, the more important that page is likely to be. If 5 people in a world with 9 sites, supposing 5 sites thought it important to link to a site, clearly there are 5 sets of people of web pages who thought that this page was important. So this page must be useful. On the other hand, supposing there's a page that links to every other page, that is somewhat profligate. I mean, it's somewhat careless linking. I mean, clearly, supposing you have 2 pages, one page has 2 outgoing links, and the other page has 8 outgoing links. So the first page has thought clearly, somewhat carefully about which pages are important and links to only 2 other pages. The second page has not, basically willy-nilly is linking to every other page. So clearly, the linking from the first page, which has more discrimination, provides more information than the linking from the second page, which is linking to every other page. So we want to use the links between the pages as a clue to how useful a page is, and we are going to measure this usefulness in 2 ways. How many pages link to a page, and among the pages linking to a page, if you have a page with somewhat conservative taste, so that it's linking to few other pages, you want to give it more importance. Okay. So much for prose, and so let's go back to our graph. Now I have taken the same graph as before, except now I have numbered each page. For example, this page, which was just called MBU, now has a number 5, and its weight symbol X5 is also written here. So I think this is not very visible. Again, I'm not. I should have had a more visible symbol here. But anyway, all that I have done is to take the previous graph and add it to the symbol and number. The numbers are assigned arbitrarily from 1 to 9, and corresponding to each number, there is also weight X5, which we have to determine. I'm keeping you in suspense. I've talked a lot, but I have not yet told you, except in prose, how the weights are determined. So now let's translate my prose into math. So these weights, we're going to get at the algorithm in 3 steps. I will first give you a first attempt, then I'll tell you why that doesn't quite work, then I'll tell you how to modify it in 2 steps. The first attempt is exactly implementing what I described in prose just a few minutes ago. You give an importance to each page depending on how many pages link to it, but if a page links to it with very few outgoing links, that has more importance. Here. Okay, now I'm going to give you a little time to internalize this, because this is at the heart of the algorithm. the weight, so the xi, so of a page, is the sum of the pages that link to it, but the contribution of another page, this sum is over j. So here I is fixed, and here the sum happens over j, and this symbol means pages that link to I. So the sum is over pages that link to I, and the contribution of a page that links to I is the weight of that page xj divided by the number of outgoing links from the page xj, from the jth page. So this is exactly what I was telling you in prose. The importance, the weight of a page is the sum over all pages of weights sum of weights of all pages that link to it. But so now let's concentrate on a page xj that links to a page I. How much does the weight of j contribute to the weight of I? It's the weight of j divided by the number of outgoing links from the jth page. I'm going to give you a minute or two to think about this, because if you get this, you will get the rest of the. See, this is really, this is really the heart of Google. Each time you are using Google, it is this algorithm, of course, elaborated and dressed, and Google is just the foundation. They have to do lots of things, spam, they have to have things to avoid spam, etc., etc. But this is the heart of Google. I will wait for a minute. If it's not clear to anybody, please ask me. Because otherwise, you've come all the way, you've spent 20 minutes listening to me. And, really it's not worth the. So please think about this. Yeah?
Why should it add up to 1?
No, that's just a normalization. This is how, once I find such a solution, in fact, you see, this will not have a unique solution. I have not told you whether this has a solution, how unique it is, but it's clear that if it has a solution, I can divide such that the sum is non-zero, then I can divide by the total sum to get a solution where the weights add up to 1, right? Because this is a linear equation. Yeah? Yeah.
It's based on the assumption that the graph has no cycles.
Oh yeah. Good, thank you. Yeah, I'll come to that. Yeah. That is one of the traps. So I told you that I'm going to implement this in 3 steps. So I think the second step deals with that. Or the third, yeah.
It doesn't depend on the number of outgoing links from I, just j.
No. See, it doesn't depend on outgoing from I, as you see in the equation.
Shouldn't it depend on, because I is the most efficient side. It doesn't go to any other side. It's not linked to any other side. If I is the most efficient.
No, that's the other problem. If you have a site that doesn't link to any other site, again, there's a problem with this, which we deal with. So the two of you have identified the 2 reasons why this algorithm has to be modified. Now, I hope you have not found a third one. Okay, tell me.
So why should each vertex contribute a fraction of its weight equally?
To the other sites?
Yeah,
because there is no other information given to
one of those sites is more important than the other.
We don't know that, right? See, as far as the computer is concerned, it's trying to deduce from the structure of just the sites and the links. That's what I was trying to tell you. There is no a priori notion of importance of a site as far as the computer is concerned. You or I, we would be able to look at the contents of a site and say, haha, this looks more interesting. But we would not be able to look at the trillions of sites, so that's not an option. So you have to have something that a machine can more or less blindly do just from the structure of the sites and the links between them. So there is no, it's not as if there is, so that's what I was trying to say. There is, going into this, you have no other measure of importance. We are trying to extract from the structure of the web a notion of importance. Yeah. Yeah.
Why should it only be a linear relationship between, why can't it decrease exponentially?
Good question. Yeah, I don't know. I mean, for all I know, Google tweaks this. There could be tweaks of this. I don't know. Yeah.
Why is not page visit being taken into consideration?
Page visits.
Yeah, the number of visits the page has. Because that's also important for a page, no?
Yeah, but page visits is not a public knowledge, right? There are some sites that choose to make it public, but not all
That
sites.
is one of the criteria for your
No,
Google's,
I know, but you need something that's publicly known. I don't think page visits usually is internally monitored within each site, and not all sites make their number of visitors public. I mean, but again, for all I know, you see, this is just the skeleton of the algorithm. I mean, Google has, I would think, literally thousands of refinements of this. Okay. So, for all I know, they do that as well. Yeah. Yeah.
Yeah, you're defining the weight as a function of the weight of another page.
Right.
So, how do you find that weight?
No, so this is, that's why somewhere earlier I had said put some words in quotations in a consistent way. You see that? Yeah. So that's the point. So this is why this is a system of linear equations. Okay, so I have explained that equation to you. I have explained the notation j going to I. I have explained the notation nj. And the idea is that each vertex contributes a fraction of its weight equally among its friends. The friends are the outgoing links. Okay. So let's contemplate this equation again. I've just written the same equation more starkly. Yeah? So the weight of the ith site is the sum over site j such that there is an arrow from j to I of the weight of j divided by the number of outgoing links from j. Okay, so now if I go back to this equation, this is where a board might have been useful, but let's just see. Let's concentrate on the first site, the one in the middle up there. So how many sites link to it? 3. There is 3, 8 and 9. And if I look at 3, it has only one link, outgoing link, so all of the weight of 3 goes to 1. If I look at 9, it only has one outgoing link, so all the weight of 9 goes to 1. On the other hand, the vertex 8 has 2 outgoing links, one of which goes to 1, so half the weight of 8 will go to 1. Okay, so that is what I have written here. x1 is x3, all the weight of 3 goes to it, all the weight of 9 goes to it, and half the weight of 8 goes to it. Okay? And similarly you will write x2 and so on, and then, so now this is when you make the first step. So that is a system of linear equations, and the way of symbolically dealing with linear equations is to take all the variables and put them together, package the variables in a column, and that becomes a vector. So you have this vector, and all the coefficients you put them in another package called a matrix. And so this symbolic way of writing is means exactly the same as those 9 linear equations. Okay, So how to read this? So many of you know about matrices and vectors, but there's nothing mysterious about it. So this tells you that x1 equals 0 times x1 plus 0 times x2 plus 1 times x3, which is what you have there. 0 times x4, 0 times x5, blah, 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 and all the way till I get to 8, 0.5 times x8, and then all of 9. Okay. And similarly, x2, you do this row and this column, and so on. So this is just that system of equations written in matrix and vector form. It's a more compact way of dealing with systems of equations and unknowns. I mean, it's more than compact because now I can think of this whole box as an object. This matrix, I mean, often I don't need to know what is inside. Just like the computer trawling the web, I don't need to know the contents of the matrix for many of the arguments. I can just think of, see, this is the abstraction that math does. Often you can take a very complicated object and just think of it like a box. And you don't open the box until you need to. Okay, now the question is, does this system have a solution? Of course, there is a solution with all weights 0. If every weight is 0, clearly the equations are satisfied. We want a solution such that not only the weights are not 0, I mean, not all the weights are 0, and we want such that none is negative, and the sum of all weights is 1. So clearly, if I can find a solution such that not all the weights are 0, and none is negative, then the sum would be strictly positive. So I can divide by the sum to get a solution where the sum of the weights is equal to 1. Okay. So now the question is, does such a solution exist? Is it unique? How do we find one? As I said, remember that in the real world, the number of sites is 60 trillion, yeah? And that's a large number of weights. So, okay, so this is what I was saying, that you're trying to solve this equation. And so those who know a little bit more of linear algebra, we are trying to find as eigenvector of this square matrix with eigenvalue 1, and all entries of the vector should be non-negative, and the vector should be non-zero. Okay. So the theorem, it's a small theorem, it's not difficult to prove because the determinant is non-zero. This has a unique solution, and I found this with the help of Mathematica. And here is a list of sites arranged in decreasing order. You see there are lots of ties. There are pages with the same weight. Okay. So here are 2 sites tied, there are 2 sites tied, etc. Okay. So there are 2 potential traps. The first is what is charmingly called a dangling node. So this is what I think you were saying. So there could be, say, in the old days, PDF documents did not have outgoing links. So if you went to a PDF document, that's it. You would be stuck there. So here is, I've changed one of the, I've added another a 10th site, and I have put these 2 links. So this site, this page has no outgoing arrows. Now, why should you be worried? So this is best understood from a dynamical point of view. So this is going to be slightly more advanced, and I like to think that I'm giving you a little appetizer for Professor Rao's talk, where he'll talk about probability. So imagine somebody who has a lot of time on his or her hands and is surfing the web quite lazily, not really bothering to look too much at each side. But basically what the person does is spend, say, a second on each side and then at random picks an outgoing link and follows that. And he or she does this for a long time, internet addiction and so on. The rule is that this person chooses an outgoing arrow with, without too much thought at random. So then the rule that takes, then if this person is at a site with some probability, so at each site there's some probability that this person is there, and then at the next instance of time, the probability will change because the person has clicked an outgoing link, and because of a rule, the probabilities at step n and at step n plus 1 will be linked by the action of A on the first probability vector. I mean, if you find this way of thinking too foreign, just relax. It's really not. It's actually very crucial to much of this, but I think at the end of it, if I have time, I'm going to do some linear algebra, which will hopefully make this worthwhile anyway. So the point is that this expresses the transition probability, and this condition is the condition that the probability does not change from one step to next. That means, okay, I'll just leave it there. Now the point is that, forget all that, but imagine this random surfer who's doing what I said, spending time without looking at each site and randomly clicking an outgoing link. Okay. Then, if he or she reaches a dangling node, suddenly he'll have to wake up because he's trapped. There are no outgoing links. Okay. So, if you believe that my search for weights has something to do with a random surfer, then a dangling node is a danger, because a random surfer can get trapped at a dangling node. Okay. So I ask you to believe that my quest for weights is the same as finding the stationary distribution of a random surfer, right? Whatever that means. But you see very clearly that the random surfer, when he or she encounters a dangling node, is in trouble, because he or she is going to be trapped there unless they wake up and consciously move to some other side. So, to take care of dangling nodes, we have to modify our recipe as follows. That a dangling node contributes an equal fraction of its weight to all the other sides. In terms of the random surfer, what it means is that whenever he reaches a dangling node, at the next instance, he just chooses one of the other sides at random and jumps to it, even if there is no outgoing link. So you instruct the surfer, okay, at any given site, for the next click, you choose an outgoing link at random and follow it. If there is no outgoing link, you choose any other site and jump to it. Okay. And actually, this works pretty well, you see, for my graph with 10 sides, I could again solve this, and I get this set of weights. But there is a second trap, which are cliques. A clique is a close group of people who are kind of like each other too much. They don't refer to the outside world. And you should see a clique here. I've taken the first graph and reversed one arrow, and the clique is here in red. If you look at these three sides, they only refer to each other. These three sides form a clique. They are, if you enter that triangle, you will not leave it. You see that? So in our random surfer, if he or she reaches one of these sites, then they're going to be trapped going round and round. So the stationary distribution would basically be 1/3, 1/3, 1/3 and 0 everywhere else. You could do worse. You could have disconnected graphs. In which case, the random surfer who begins with one of these graphs is going to stay there and not sample the other web. So if the World Wide Web were consisted of, say, one country and other countries which just don't want to talk to each other, then the person in the first country and the person in the second country will not know about the existence of the rest of the web. So, so a third attempt is we modify our rule again. So this gets basically what you need to do is well, what I said there. Okay. Let me give you 3 minutes to read it. So let me recall, B is the rule modified by the rule to take care of dangling nodes. Okay. Now I am modifying it again to take care of peaks. Okay. I think people are maybe a little tired, and I am also running out of time. So okay. Okay. So now this I will go to the blackboard and tell you how to find this eigenvector. You know. So what is behind finding the eigenvector? Okay. And here are a couple of references. Now, if Shankar can come up and Shankar. So I'm going to now do some linear algebra. If there are questions about the Google algorithm, maybe it's a good time to. So the third step I intentionally rushed through, okay, because that, I don't want to overload you with information. But I hope the lesson is clear. You have to take care of dangling nodes and you have to take care of cliques, and Google has very obvious ways of dealing with them. So, we are interested in finding an eigenvector Ax equal to x, where A is a very special kind of square matrix. Okay? So this is after the second modification. A is, so A, if I write it as A is Aij, so A is a square matrix n by n. And each term is strictly positive after the second modification. So this is why I'm feeling a bit sorry that I hurried through that. But the effect of the second modification is to make each term strictly positive, and the sum of in every column, the sum of the elements in the column is equal to 1. A, I, J, where I sum over I is equal to. So fix J. So if I take the jth column, the sum of the entries in this column is equal to 1. Okay? And we want to solve for this, and so this is actually, so this is a baby version of a famous theorem called Perron-Frobenius, and that guarantees that in fact there is a unique solution. So this is baby there exists unique solution x x1 xn xi bigger than equal to 0, some xi equal to 1, actually xi I think bigger than 0. And the best way of seeing this is to think geometrically. Okay? So let's consider n equal to 2. So I have x1, x2, and consider. So this is a vector x. And let's look at vectors x that satisfy xi, well, let me put bigger than equal to 0 and the sum equal to 1. So what that set is this. This is 1, 0, 0. Okay. Now take any vector on this and apply a to it. Okay. So I'm going to draw something wrong and then I'll correct it. So this is, no, let me draw it very wrong. Then I'll correct it. X. And Ax is another vector. Okay. So all that I've done is taken vector that lay on this line segment and applied the matrix, multiplied it by the matrix A. And actually, this is the wrong picture. It turns out that with these conditions, what A will do is to map such a vector to some point here. So A maps, first lesson, A takes any point on this line to another point on the line. But it does even better. So supposing I take this point, 1, 0, where it will map it to, okay, so I'm sorry, I should draw my vectors 1, 0, 0, 1. What is that? This is just A11, A21. Okay. The effect of acting on this vector by A is the first column of the matrix A. Now, these guys are both strictly positive and the sum is equal to 1. So that means that this vector has to be somewhere inside this line segment. It can't be this, it can't be this. It has to be inside this line segment. And similarly, if I act on with A on 0, 1, so this is A 1, 0, and this would be A 0, 1. So the effect of acting with A on this line segment is to shrink it to this line, this part. Now if I apply A to this once more, I'll get a smaller line segment. So as I keep applying A to the line segment, I'm going to get smaller and smaller line segments until the eigenvector gets captured in these shrinking line segments. And this argument works in arbitrary dimensions, and you basically, well, you shouldn't call it a quadrant. In 3 dimensions, it will be an octant. In 10 trillion dimensions, it will be 1/10 trillionth of that space. That fraction of that space gets, under the multiplication by the matrix A, gets sharper and smaller and smaller until the eigenvector gets trapped in the intersection of these guys. So this is how Google finds weights of the sites, and that is how it ranks pages. Now clearly, when you are handling matrices which are 10 trillion, 10 trillion times 10 trillion, you need sophisticated ways of handling them. This is where numerical analysis comes in. Now, what works in Google's favor is that most sites link to very few other sites. So this matrix, before you do the modifications that I suggested, is what's called a sparse matrix. It's a matrix, it's a huge matrix, but most of the entries are 0. So you are working with sparse matrices, and numerical analysis knows how to handle sparse matrices. There are very, very clever ways of doing these. So numerical analysis, linear algebra, computers, storage, this is all goes into the mix. Thank you.